actually do the live feed and all. Just one request. In case you end up hearing some gali in between, you mute me off because we are in traffic. People may end up getting scolded right. They come on the wrong side.
No problem, no problem. It is done now.
Yeah,
we'll begin.
Just one request.
Good afternoon, one and all. I welcome all the participants for the second session of the first day of the 5-day FDP. The present speaker is Dr. Arulalan Rajan. I'll just give a brief introduction about the present speaker. I think he needs no introduction. He has already delivered several talks across India in most of the institutions for all the levels, I believe, from school to all the UG, PG and research scholars as well. So in spite of that, it's my duty to introduce the present speaker. He holds PhD from IISc Bangalore, Indian Institute of Science. He had been a part of Tektronix India and had been a trainer in corporate houses including LG Soft, Sony, Tektronix, L&T Infotech. Dr. Rajan was an assistant professor at NITK Surathkal during 2013 to 2019. Currently, he is a faculty for the Proficiency Program, Indian Institute of Science, Bangalore, teaching courses on mathematical foundations of machine learning and on probability foundations for machine learning to working professionals on Saturdays and Sundays. His research interests include applied number theory, linear algebra and applications, signal processing and applications, and etc. On professional front, he has co-authored a book on linear ICs and applications published by Texas Instruments. He has also done the Indian adaptation of the book on a friendly introduction to probability and stochastic process by Yates and Goodman for Ville, India. I now welcome the professor, present speaker, Dr. Arulalan Rajan, and deliver a talk. Please,
thanks
sir.
a lot, sir. Thank you, sir. Thank you. Thanks to GR, sir, and thanks to the entire team at Ramaya. Thanks for giving me an opportunity now to be a part of your workshop again. So good afternoon all. Good afternoon to the audience. So it's a nice time after lunch, I guess. I'm quite sure most of you would have had some good food. Probably waiting for a good nap also. I'm not going to give you that happiness of probably having a nap. So I'll be doing the mathematics part of it, but mathematics is something which scares everybody. So I'm going to do the mathematics of cryptography, and that's what I was told, that I should probably be doing the mathematical foundations of cryptography. So what we'll do is we will start with what we know about numbers. We'll look at numbers a little bit, and then we'll look at interesting things about the numbers playing a role for, as part of cryptography. So the first thing that we all know about whenever we are taught as, whenever we begin our school or probably, first formal introduction to mathematics or something, we always talk about numbers, right? So we always talk about, I hope my screen is visible to everybody and what I write is also visible. So we always talk about numbers. And the first thing that we are always start is basically look at, okay, we don't straight away start with, like what engineering kids do, start some hyphen, do jargon as far as numbers are concerned, or for any concept, as far as any concept is concerned. We start with, the notion of, let's say, numbers. And we say that, okay, our teachers would have probably said, like, say, start counting from 1 to 10. So we are basically taught how to count, right? The first set of numbers that we basically look at are counting numbers, okay? So we start with counting numbers, and then we move on counting numbers, and then we move on to what we call as measuring numbers. These counting numbers are basically your whole numbers and whatever we have natural numbers and stuff. So the next one that we look at is like, no, we don't want to look at this anymore, but we want to look at real numbers. When counting numbers itself kind of gives us a horror story, real numbers are going to make it a bigger mess, because when somebody tells you, pi is a real number, they say it is 22/7, and when you reach some level of maturity, mathematical maturity, typically we feel that pi is not exactly equal to 22/7. Pi is approximated by 22/7. So we have all kind of stuff. But before that, when we even before getting into the even before getting introduced to what we call as real numbers, we would have also had this. As far as counting numbers is concerned, we would have had the idea of prime numbers and composite numbers, right? So typically we say that any number whose factors, for that we should know what factors are. So when we look at, we basically classify this as odd numbers, even numbers, prime numbers, and composite numbers, and so on, right? Prime, composite, etc. Now the problem here is, when someone talks about prime numbers, the very first definition that we would probably have looked at in terms of prime numbers is, look, they're the most boring numbers, right? Boring numbers in the sense, because prime numbers do not have any factors other than itself and the number 1. So we say that prime numbers, no factors other than, for example, no factors. Or why we say negative? Well, let's say factors are only itself. So let's do that. Factors or divisors. Divisors are the number and 1. There are no other factors. So this is the kind of boring numbers that we really look at. At school, when somebody asks you to do anything with prime numbers, I'm quite sure you would have really bothered, because it's say, okay, fine, this is such a boring stuff. Why boring stuff? Because I don't get to learn anything interesting out of it. It keeps saying, look, these are the 2 factors that I have. But it would have been a nice idea if the same teacher would have probably taught you mathematics. Would have said, look, prime numbers, they have another interesting property which you can infer from yourself. What is that? It says that the sum of the factors of a prime number is basically the immediate successor of the prime number. If somebody had told that, then I think probably our life would have been much easier, right? That would have been that would have actually given us another dimension to our idea about prime numbers. And probably if somebody else had told you, like, if you have any composite number, or for that matter, any number that you take, any integer that you take is either prime, probably if somebody had told you, look, the first thing is sum of divisors of P for a P prime is equal to P plus 1. That means we are going to look at, what is that? The immediate successor. The immediate successor of P. Or probably if this was one of the other dimensions of looking at, let's say, prime numbers. These are probably certain stuff which if we had made certain observations as far as the numbers and stuff concerned, then our life would have been much more easier. We would have developed a strong liking for mathematics. The second thing is, like, okay, suppose if somebody tells us, look, it's not just about this. Even this works. What is that? Every integer is a prime. Every integer n greater than or equal to 2 is a prime, or is a prime, or product of powers of prime. If somebody had told this, then probably we would have made our life much easier. We would have started again. We would have started our exploration in prime numbers. But unfortunately, we always leave the exploration about prime numbers to the hands of mathematicians that engineers typically forget about all these things. So product of powers of prime. Okay. No, it is not just that it's not just these three properties, but prime numbers come with phenomenally interesting properties, phenomenally powerful properties, which actually form. If on this day we are able to make a payment in Amazon or probably in Flipkart, or probably we are able to do an online transaction, when you send some money to your near and dear, if it all numbers make it more and more simple, and it all works majorly because it stands on a strong mathematical property, right? So we're going to look at that in this. Probably I'll try to go a bit fast on this. If there are any questions, you could post it in the chat box or the comment section, where probably the organizers can get back to me with the questions, which I'll try to answer. Okay. With that introduction, what we'll do is we will go ahead with today's lecture. This is okay. Okay. So, what are we trying to do? Why should we look at prime numbers? I'm going to show you some interesting properties of certain numbers first of all, and then let us try to look at what is happening. And let's try to extrapolate this and see how many more rich properties of primes come, and what are those rich properties which enable us to actually do our modern security, or what we call as cryptography. So the first thing that we're going to look at is the following. The first thing we're going to look at is what we call as prime arithmetic. I wouldn't talk about divisor. Okay, the first concept that I want to look at is basically the greatest common divisor, which we call as GCD. Right? We're going to look at the greatest common divisor, or GCD. What do we mean by greatest common divisor? Suppose you have suppose you have two numbers, A and B. Now, what I want to do is I want to list out all the divisors of A and B together, and I want to see what are all the common divisors. All the common divisors of A and B. Now, what we do is, among the common divisors, you find out the largest, and that becomes the greatest common divisor, or the highest common factor, which we all know. So, take integers A and B. Now, what we do is list out the factors. So, list out divisors of A, divisors of A, and divisors of B. Now, what we do is pick the collects, pick the fellows who are common. Pick the common fellows. Pick the common fellows. Find the maximum among them. Find the largest. And call that fellow as a GCD. Okay. Now we have one more thing that we need to see. Why am I interested in this GCD. Why should I be interested in the GCD? I hope it's fine if I close down my video for some time. Okay. Yeah. Okay. Let's consider some examples. Numbers 5 and 25. What are the factors for 5 and 25? For 5, it is 1, 5, and for 25, 25, I'm going to write as 1, 5, 25. Is this right? To us, look at the set of common factors here. Look at the set of common factors here. What are the common factors? The common factors are basically 1 and 5. Now, what we do is choose the greatest one here. What is the greatest fellow here? Greatest fellow is 5. And that is going to be your greatest common. So 5 is going to be the GCD. Now, suppose I take another example. Let's take a second example, where in which I'm going to look at numbers which are like 7 and let us say 620. Take 620 and 7. These two don't seem to have any common factor because 7 has a common set of factors which are 1 and 7. And 620, I know it is some set of big numbers wherein which none of them related to 7 come into picture. So what we say is, okay, so now what we say is the greatest common divisor is 1. Now the idea behind this greatest common divisor is that we can actually define two numbers to be relatively prime or co-prime if they have the greatest common divisors to be 1. And these co-prime numbers or relatively prime numbers are the ones which are going to play a very, very important role. Okay, so we say that if the GCD of A and B is 1, we say that A and B are co-prime. A and B are co-prime. So why do we want to look at this co-prime? We will see the co-prime numbers, or we say relatively prime. Now the reason that we want to do this actually comes out very well because it's only for relatively prime numbers we end up defining something. We can define a lot of interesting mathematical terms. Let's look at what they are. Okay, I hope the idea of GCD is clear. What we're going to do is we're going to take a few things here. What is that? We're going to look at modulo operations here. We're going to look at modulo operations here. Let's see what it means. Modulo operation simply means that you take two numbers A and B, whichever is the smallest number, you divide the biggest number by the smallest number and try to get the remainder that the biggest number leaves when you divide by the smallest number. And that is what we're going to call as the residue. And we're going to say A is equal to say some R mod B. So let's write that. For example, so we say that A is equal to B mod M if A can be written as a multiple of B plus some remainder R1, where R1 is strictly less than B and just less than 0, less than R1, less than B. It's a number which is greater than 0, which is less than B. So now this is exactly what we use this notation. This is called congruent to this triple horizontal lines. We say that this is what is congruent relation. Now, what we're going to do is, from here, where do we go? I want to look at, let's take this. Suppose I want to look at modulo 5 operation. Modulo 5, addition modulo 5. Now, what do we mean by addition modulo 5? You take any two numbers, add them, and then divide by 5, find what are the remainder that you would get. So that will throw us something very, very interesting. So the set of possible remainders that we have here are, let's say, what are the set of remainders that we get? Set of remainders modulo 5 set of remainders modulo 5, we will get all numbers from 0 to 4. This is right. 0, 1, 2, 3, 4. Now, what we want to do is, I want to add two numbers. Say, for example, I take this number 7 and then add a number 9. Now, what do I do? And then I want to do a modulo 5. So this simply means it is 7 modulo 5 plus 9 modulo 5. 7 modulo 5 is whenever you divide by 7, the remainder you're going to get is 2. Whenever you divide 9 by 5, the remainder you're going to get is 4. And then you do a modulo 5. So you're going to get 1 mod 5. Again, I have to use this congruence notation. Okay. So the idea behind this is there are two interesting stuff. Whenever we do modular arithmetic, we always get into a very interesting stuff wherein which the arithmetic on very large numbers will basically be converted to arithmetic on smaller numbers. Is that okay? Now, with that in mind, now what we want to do is, I want to do this modulo 5. Let's look at what's happening quickly. So I have numbers 0, 1, 2, 3, 4. And I'll write those numbers again, 0, 1, 2, 3, 4. Now what we see is, if I add these two fellows, every row element with every column element and then do a modulo 5, let me see what I get. So we get 0, you add with this one, it becomes 0, 1, 2, 3, 4. If you add 1 with all these elements, you get 1, 2, 3, 4. But then there is something interesting that happens here. 1 plus 4 is 5, 5 mod 5 is 0. So you get 0. Similarly, you do this 2, 3, 4, 0, 1, 3, 4, 0, 1, 2, and 4, 0, 1, 2, 3. Now, from here, I go on to look at what is called as, I'm going to look at this, let's see, I'm going to look at this fellow who is across this diagonal and see what is happening with it. This diagonal, it says, you add this element, for example, with this element, you end up getting a 0. So when do we get a 0? When we add two numbers, one number is the negative of the other. For example, you take the number 7, you have to add negative 7 to get a 0. Now, what we have done is, we have basically done 7 plus 10. What we do is, we do 7, instead of doing, we do 2 plus 3 and then go on 5. That's a 0. Of 3, and 3 is the additive inverse of 2 as far as modulo 5 is concerned. So let's write that. So 2, 3 are some pairs. 2, 3 are related. We say 2 and 3 are additive inverses. Additive inverse modulo 5. Mod 5. Okay. Similarly, we can say 1 and 4 are additive inverses modulo 5. And this additive inverse keeps changing for different numbers, different modulo that you take. The additive numbers, we all know that it keeps changing. Now, let's look at one. It's not kind of addition. I also go ahead doing my multiplication and see what happens with multiplication. Okay, so let's do quickly what happens with multiplication. 0, because 0 into anything is going to be 0. So I don't have to use 0. and then to multiply every element in the column, then do a modulo 5. Okay. Just a minute. Just 1 minute. Just 1 minute. Hello, am I audible?
Yeah, yes, sir. Yes, sir. Now it's very clear. You just go ahead.
Audible, right? Just give me a minute.
Yeah. Go ahead. Go ahead.
Really sorry for it.
No problem. No problem. Go ahead, sir.
Hello. GR sir, is it okay?
Your screen is unshared now.
Yeah. So it comes with a new whiteboard. Okay, that's fine. I'll still go ahead.
Yeah, fine. Carry on.
So I'm going to do modulo 5 multiplication. So what I'm going to do is I'm going to look at this. I said we'll forget 0. So we're going to look at 1, 2, 3, and 4. 1, 2, 3, and 4. So I'm going to multiply each of this fellow with each of this fellow, and then I'm going to do a mod 5. So I'm going to get 1, 2, 3, 4 here, right? And here I'm going to get 2, 4. 6 mod 5 is 2 into 3 is 6. 6 mod 5 is 1. Then I'm going to get a 3. Then I'm going to look at this 3. Again, it's going to be 3. 6 mod 5 is 1. Then I'm going to get 4. Then I'm going to get 2. Then I'm going to have 4. 4 into 1 is 4. Mod 5 is 4. 4 into 2 is 3. Then 2 and 1. Now, here I see something very interesting happening. Like how we figured out that when we added one particular row fellow with another random column fellow, you ended up getting a 0, and we call that to be the additive inverse. We see that here I take this number and I multiply with this number and do a mod 5, I get a 1. In normal terminology of numbers, when will we get a number 1? When A and B, you want to multiply and you want to get a number 1 out of it as a product. What is it? What is it that we need to have? We should have A to be the multiplicative inverse of B, or B to be the multiplicative inverse of A. So suppose if I say if A into B is equal to 1, then we say A is the multiplicative inverse of B, and B is the multiplicative inverse of A. This is what we typically say. Is that right? Now, the same way we see 1 here in different columns. So we are going to call this particular, I mean, you take that corresponding row and the corresponding column in which we get a 1, you say that these two are multiplicative inverse pairs. Multiplicative inverse pairs. Now, what is interesting is, suppose if I just change this number modulus 5 to, let us say, modulus 6. I want to do mod 6, then I'm going to see something interesting happening. 1, 2, 3, 4, and 5. I'll do the same thing here. 1, 2, 3, 4, and 5. What am I going to get? I'm going to get something interesting. This is going to be 1, 2, 3, 4, 5. This is going to be 2, 4. 6 mod 6 is 0. 8 mod 6 is 2. 10 mod 6 is 4. 3, 0. 3 into 3 is 9. You get 3. 3 into 4 is 12. 12 mod 6 is 0. So you get a 0. Then 3 into 5 is 15. So you get residue, remainder 3. Similarly, you take 4. This is going to be 4. 4, 2 is 8. You get 2. 4, 3 is 12 onwards. It is 0. Then 4, 4, 16. It is 4. 4, 5, 20. You get 2. Then similarly, you have 5. 5, 2 is 10 is 4. 5, 3 is 15 is 3. 2, and 1. Now, in this, I find something very, very interesting. What is that interesting that I find? Here, at least every row had 1 or every column had a 1. I don't find that particular factor happening, that I don't see that fact here anywhere. These 3 rows don't seem to have that 1, whereas this fellow and this fellow seems to have 1. Therefore, what we say is, we say that there are only 2 numbers in the set of remainders that you get with 5, which will yield, which will, when you do a modulo 6, which will have multiplicative inverses. What are the numbers which will have multiplicative inverse? We see that 1 and 5 are the only 2 numbers, that have multiplicative inverses mod 6. Now, why is this happening? It is happening for a simple reason that the other numbers, they share a GCD with 6, which is more than 1. For example, you take 2 and 6, the GCD of 2 and 6. Look at the application of GCD here. The GCD of 2 and 6 is 2, 3 and 6 is 3, 4 and 6 is again 2. It is only those places that I don't find a 1. Instead, I find a 0, which is quite surprising because I don't see a 0 at all in the previous case when I do mod 5. Therefore, this idea of co-probability comes into picture. So what we say is multiplicative inverse of, let us say, A mod M exists if and only if A and M are co-prime. This is not a problem if you take M to be a prime number and A to be any number less than this prime number, because A and this prime modulus, they are not going to share anything in common. Therefore, they're all the, with respect to this prime number, every A will have a multiplicative inverse. Whereas the moment you take M to be a composite number and then you look at numbers less than this composite number, multiplicative inverse ceases to exist. Therefore, the idea of coprimality comes into picture here. This is the very important application of coprimality that we look at. Is this clear? Now, going ahead, we're going to see something more. It's not just about this multiplication and stuff. Okay, before we even go into that, let's look at one important property here. And let's see what happens. Okay, so this was basically 1, 2, 3, 4. Now, observe each row in this case. When in this table, this is modulo 5. Please observe each row in this case. Is there something interesting that we see? Every row is basically a product of numbers. If you look at every row and try to take the product, it is of the form 4 into 3 into 2 into 1, right? The first row is the product of 1, 2, 3, 4. Second row is the product of 1, 2, 3, 4. Third row is 1, 2, 3, 4. And fourth is also 1, 2, 3, 4. Now what I do is I do a mod 5. If I do a mod 5, then what should I get? That is very interesting. We saw from this table itself, there is something happening. if I multiply 2 and 3 together, I will get 6. 6 mod 1, 6 mod 5 is 1. So that is gone. So what I get is 4 mod 5. Is this okay? I get 4 mod 5. This is a very interesting thing. Suppose you are given a mod. Suppose you are given a mod. It's also a test for checking whether an integer is prime or not. What you do is you look at p minus 1 factorial. That means take all the numbers which are less than this particular modulus p, which is a prime number. Find the product of the entire set of these fellows. That means the set of remainders that the prime number p leaves. And then what you do, you now take a modulus over p. So what you do, you say p minus 1 factorial. We see that it is equivalent to p minus 1 itself, mod p. That's what we see here, no? 4 mod 5. You wanted to take 5 minus 1 factorial. We ended up getting that to be 5 minus 1 mod p. This is quite interesting. It's a very, very interesting result. Is that clear? I would say mod 5 here. Okay. Is this okay? Is everybody, are there any questions as far as this is concerned?
I think
is my audio?
It's going on well.
Yeah, yeah. Is my audio fine?
There's no problem, everything is fine.
Oh, that's great. That's great.
Yeah, please go ahead.
Yeah, sure. Now, going ahead, I'm going to do something more. I want to somehow, I am not happy with this multiplication because it seems to be a very elementary operation. I want to prove that, I have gone from school level to, let's say, engineering level. And therefore, I want to look at some higher mathematics because that's where all our modern technology and stuff comes in. So what we do is, let's look at this. But I'm going to take a bigger number and probably I'll take a few minutes to write down. And then I'm going to ask you a few questions. Okay, so let's do this. I'm going to look at modulus mod m, where m is equal to, let us say, 7. Okay. And I want to look at the set of remainders mod 7, which is basically the number, say, 0 to 6. Okay. 5 and 6. And I don't want the 0 for some reason because 0 power anything, this thing, don't really want to work all that. So what I would do is, I would basically consider this set from 1 to 6. And what I'm going to do is exactly like what I did, but I'm with a twist. It's like what they say, no, what is that? Mad angles. So what we do, we're going to do it with a twist. What is the twist that we're going to do? I'm going to call these along the columns, I'm going to call them as number I, integer I. The numbers are going to be 1, 2, 3, 4, 5, and 6. And along the rows, I'm going to write this as A. I'm going to write this as 1, 2, 3, 4, 5, and 6. Now, what I'm going to do is interesting. I'm going to do the following. What is it I'm going to do? I'm going to look at A to the I mod 7. I want to look at A to the I mod 7 and see if I can find something interesting. Let us see what happens. A to the I, 1 power 1 is 1, 1 power 2 is 1, 1 power 3 is 1, 1 power 4 is 1, and so on. Similarly, 2 power 1 is 2, 3 power 1 is 3, 4 power 1 is 4, 5 power 1 is 5, and 6 power 1 is 6. This is all done. What I need to do is I need to fill in this set of columns. What is it that I get? Let's see what happens. So 2 squared is 4, 4 mod 7 is 4, 2 cube is 8, 8 mod 7, 8 mod 7 is 1, 8 mod 7 is 1. Then 2 power 4 is 16, 16 mod 7 is 2. Then 2 power 5 is 32, mod 7 is 4. 2 power 6 is 64, mod 7 is 1. Is that okay? Okay. Similarly, let's take 3. Okay. 3 squared is 9. 9 mod 7 is 2. Then 3 cube is 27. 27 mod 7. What is 27 mod 7? Oh, I'm getting 6. That's fine. Then I'm going to get a 4. I mean, I'll just fill this because another 45 minutes I have to finish this. So I'll fill this 6. Then 4 3 is 12 is 5, and this is 1. Similarly, if I take 4, 4 square is 16, 16 is 2, 4 cube is 64, it is 1, so it is 4 to 1 again. 5 square is 25, which is 4. 5 cube is 20, this is 6, 6 5 is 30 is 2, 2 5 is 10 is 3, this is 1. This is going to be 6 1, 6 1, 6 1. Okay, now seems to be something interesting happening here. What is it that's happening? One important observation that I make is, forget about the first row. First row is because it's all power of 1. So it doesn't make any difference to us. But the last column seems to be very interesting. What is happening with the last column, irrespective of whether you take the number 1, number 2, 3, 4, or 5, or 6, when you do this 1, 2, 3, 4, 5, 6, etc., power 6, and then do a mod 7, all of them seem to be giving me the answer 1. This goes under a very important and a very interesting theorem, which we call as Fermat's little theorem. So Fermat's little theorem. So what does Fermat's little theorem say? Fermat's little theorem says, you take this a power p minus 1 is always congruent to 1 mod p, where p is a prime number. P is a prime number. Is this okay? Now the question is, why should, see, when we started this lecture, we said prime numbers are the most dull numbers. We said prime numbers are of no use. But you see, when we try to work with prime numbers, we actually get a lot of interesting properties. We are trying to unearth a lot of properties, right? So that's what makes prime numbers more and more interesting. We don't even know how many more properties still exist. It's a gold mine, you know. Once we start exploring prime numbers, we are definitely going to get something more interesting, something new every time that you try to dig the treasure box of prime numbers. Now, my question is, oh, will this work for a composite number? This seems to be working for prime number. Suppose I change this. Let's look at that. Okay. Let's look at this. Before we even go into this, let's make one small observation and then go ahead. Okay. So what is the observation that I want to make? I want to tell this. You look at the row corresponding to 3 and look at the row corresponding to 5. There's something interesting happening here. If you look at row corresponding to 2, there's nothing great. If you look at the row corresponding to 2 or 4 and 6, we feel that, okay, what's so great about it? It is 2 4 1 and that pattern repeats. It is 4 2 1 and the pattern repeats. It is 6 1 and the pattern repeats, right? Whereas you look at 3 and 5, something interesting happens. There's no pattern at all. There's no pattern in the sense it gives me all the 6 integers from 1 to 6, right? You have this in mind. There is some important terminology that I'm going to give right now. So just let's look at this, and then I will go for a more general version of Fermat's theorem. Now, what we're going to say is, if you take the numbers 3 and 5, you take the numbers 3 and 5, and then you do a 3 raised to I mod 5. I basically in the set 1, 2, 3, oh, 3, okay, 7, sorry, mod 7. I is equal to 1, 2, 3, 4, 5, and 6. We get back the same set of integers, but in a different order. What is the order that we get? We get 3, 2, 6, 4, 5, 1. Oh, this is interesting, right? Similarly, let us look at this. Let's look at 5 raised to I mod 7. If you take 5 raised to I mod 7 for the same values of I is equal to 1, 2, 3, 4, 5, 6, what is it that we get? 1, 2, 3, 4, 5, 6. What is it that we get? We get another set of interesting thing. What is that? It is the same set of numbers, but in a different order. It says 5, 4, 6, 2, 3, 1. Basically, whatever that you try to do for this and this, you see that the set of numbers that you get as a result is a permutation of the exponents that you have taken. That means I'm getting all the integers in the residue set modulo 7. We call the numbers 3 and 5 to be primitive roots modulo 7. Why are they called primitive roots modulo 7? That's because these are the numbers which, when you try to exponentiate with the set of integers from 1 to 6 or set of integers modulo 7, you get back all the numbers from 1 to 6. These are called primitive roots mod 7. It also goes by another name. These are also called as generators modulo 7. This is okay. These are called as generators mod 7. Now, what's interesting? This is all fine. Generators mod 7. I've still not even come to the idea of cryptography. Where is all these things used in cryptography? You've been showing some numbers, you've been showing some patterns. Where the hell is cryptography here? Don't worry. If you want to do all that, I mean, you could even open your Facebook browser now. I mean, on the browser, you could open Facebook page or probably Gmail page or any other page where you have to do a HTTPS, secured transmission or secured login that you have to do. You will see this. You will see this generator. You will see this modulus. Your public key encryption scheme involves these generators and modulus. But only thing there is, the modulus need not be a prime modulus. They actually take a composite modulus. Okay, it's a bit. I mean, I will just do that in a few minutes. But I hope the idea of primitive roots is very clear. Now, the question is primitive roots. How many primitive roots? Say, for example, I tell you, here is a quadratic equation, and then I ask you how many roots are there for the quadratic equation. I mean, everybody knows quadratic equation has 2 roots. That's the 2 places where the quadratic equation hits a 0, right? Similarly, if I say cubic equation, I already know there are 3 points at which the cubic equation it's a 0. Now the question that I ask is, how many primitive roots exist for a modulus? Oh, that's a very tough question, because we need to know what's a primitive root. And the second thing is, I'll make it more complicated. Suppose I give you a quadratic equation, then I ask how many real roots does it have, how many complex roots does it have, right? So we need to answer a lot of questions. The same way here also, what we do is we try to figure out how many primitive roots exist modulo 7 or modulo prime. Okay, so we are going to say, of course, these are very subtle things. And if the audience is in general engineering audience, I mean, it's a very important, I must not say advice or whatever. Being engineers, it is always nice to make certain observations before we actually jump into the field. So observation is very, very essential as far as engineers and researchers are concerned. And therefore, as far as these primitive roots are concerned, we need to make a lot of observations. With this simple example, I will tell you certain things which are very, very subtle. Okay. Now, so this primitive roots, how do we get? We have to define this primitive roots in a proper way. What is that? Let's write that. So primitive roots of, what do you call it? We would say that A is a primitive root modulo P if and only if A power I is equal to 1 mod B implies I is equal to P minus 1. What does that mean? I am trying to exponentiate this integer A with different values, let's say I. Now, what is it that I'm looking forward for? I'm looking forward for that index at which I will get a 1. Now, if you look at the number 2, I get a 1 at 2 cube. If you look at the number 4, I get a 1 at 4 cube. And if you look at the number 6, I get a 1 at 6 squared modulo 7. If I do, I'll get a 1, which is much earlier to the 6. The only place where I should get I is equal to 1 mod p, I mean, a to the I is equal to 1 mod p or congruent to 1 mod p implies I must be equal to p minus 1. There is no other place where I can get a 1. Is this clear? There is no other index I for which I get a power I is equal to 1 mod p. So this is exactly what it means. So a primitive root is nothing but that integer modulo p or modulo m for which a power I, the smallest exponent. So this simply means the smallest exponent. The smallest exponent for which a power I is congruent to 1 mod p is I is equal to p minus 1. Is this okay? This is how I define my primitive roots. Now I ask a question. See, for mod 7, we said that 3 and 5 are primitive roots because you exponentiate them, you end up getting a lot of, you can end up getting all the integers between 1 and 6. Is that right? Now, what I'm going to ask is, how many primitive roots exist? How did we know that there are only 2? We actually made an exhaustive table and we said that, look, this table shows that there are only 2 rows at which in which you get all numbers from 1 to 6, and therefore you call them as primitive roots. So what we say is the number of primitive roots is very interesting. I'll write that just a minute. I'll erase this just a minute. Just one, sorry. GR sir, is everything fine?
Sir, yes, sir, yes, sir, it's fine.
Yeah,
instead of erasing, can't you take a new slide? I mean, new sheet.
Okay, I'll try to do that.
That may be better. We can move.
Yeah, because
we can keep a record of all these and we can save it also later, I believe.
Okay, because it's the first time I'm doing with this. I used to do it with OneNote and notes on iPad, but this whiteboard I went check, so I really do not know how this works. Yeah.
Fine. Okay, continue, no problem.
Yeah, so I'll go ahead with this.
Yeah.
Okay, so now we define something called as Euler totient function or Euler phi function. Now, what does this mean? Suppose I give you an n and then I tell you find phi of n. This basically returns the number of integers less than or equal to n and relatively prime to n or co-prime to n. For example, you take n is equal to 7, then you list out all the numbers less than or equal to n. What are the numbers? We have 1, 2, 3, 4, 5, 6, and 7. Now, out of this 7 numbers that we have, knock off all those numbers which have a GCD which is not equal to 1 for this, which is that 7 and 7 don't have a GCD 1. Rest all numbers are, they have a GCD 1. Now, what is happening? I'm going to look at the count of this set. So, totient of n is basically the number of integers which are less than or equal to n and relatively prime to n. So, this is going to be 6. So, we're going to say totient of 7. Sorry. totient of 7 is 6. Let's take one more number, n is equal to 16, and see what happens to this. Some random number we're going to look at. So I'm going to write all these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Now what to do? Knock off all those fellows which don't have a GCD 1 with 16. 2 is gone, 4 is gone, 6 is gone, 8 is gone, 10, 12, 14, 16. All these fellows don't have a GCD 1. Now count the number of elements that are left out. What is that number? We see that the number is 8. 1, 2, 3, 4, 5, 6, 7, 8. So totient of 16 is 8. Now what we are going to say is, now the idea of totient function is clear. So what is it that we're going to say? We're going to say the following. We say that A is a primitive root mod P if and only if the smallest exponent I for which A raised to I is congruent to 1 mod P is I is equal to P minus 1, which is equal to totient of P. For any prime, the totient function is P minus 1. So this is what it means. Okay. Now, this may be a bit difficult to understand considering the time that we have. This may be a bit difficult to understand, but the general idea is this. So why did we even do this? We were looking at the number of primitive roots. Number of primitive roots modulo 7. We saw 2 of them. What were the 2 numbers? They were 3 and 5. Right? They were 3 and 5. How did we get this count 2? You can actually verify very easily that the number of primitive roots is given by totient of 7. So this is the formula to find out the primitive root. You can check that totient of 7. What is totient of 7? Totient of 7 is 6. What is totient of 6? We'll just check totient of 6. Totient of 6 is basically the count of this set. 1, 2, 3, 4, 5, 6. Again, knock off all those fellows whose GCD is not this. So this is equal to 2. So you can prove this very easily. It is totient of 6 is equal to 2. Is this clear? Okay. Now, why did we do this again? Now, with this in mind, let us see what happens with our modern cryptography. Is this okay? Are there any questions or any doubts that we have now? Any questions? Anybody has any question, comments, or something like that?
No, sir. At the end, we'll have for a few minutes. If at all someone post that in the chat box, we'll just have it. Because the participants are not listening to this through Zoom. They are listening to this through YouTube.
YouTube. Okay, fine. No problem.
Yeah.
No problem. No problem. Yeah. This is fine. Shall we go ahead?
Yes, sir. Fine. Go ahead.
Yeah. So now comes the idea of modern cryptography. What is modern cryptography? Whatever that we're trying to do for our secure transmission or over the channel and stuff. Let's look at that. So let's look at that. So how does modern cryptography works? First of all, what do we mean by modern cryptography? That's a good question to ask, but let's look at this. We say that first works purely on strength of mathematics. What do we mean by that? For example, I tell you this number, let's say, let's take this example. Given n is equal to, let's say, 56. Find the prime factors of n. Find the prime factors of it. So what do? You list out whatever the divisors of n are. So we say that n is equal to 56, which is nothing but 7 into 8, which is nothing but 7 into 2 cube. Therefore, the factors are, the prime factorization is basically, what did we say in the initial stage? We said that either an integer is prime or the integer is a product of powers of prime. This is basically the prime factorization that we have. Now, suppose if I give you a 2-digit number like this, it is easy to figure out the prime factorization. Suppose I give you, suppose we give you, it's a 600-digit n and ask for prime factorization of the same. This is going to be an exponential time problem because we really do not know what is the 600-digit number. Suppose if it's an even number, then it is easy in one sense because you can divide by 2 and then get that other number. Suppose if that were also equal to, even number, that you can completely keep dividing by 2 and so on. Suppose if that fellow is turning out to be, an odd number, then you have to check whether it is divisible by 3, divisible by 5, 7, and so on. You have to keep dividing by every other fellow. Is this okay? So the problem comes there. So what we do is we say that, okay, given a 600-digit number, it is impossible to, find the prime factors in polynomial time. That's what we have. Normally, we talk about this, polynomial computation, NP complete, NP hard, exponential time. So this basically, prime factorization is an exponential time problem. So we should say prime factorization to find the prime factors of a given integer is a non-polynomial time problem. That means this is gone. So this is going to be computationally extensive. Okay, so this is not going to work. Therefore, what we do is the first thing that people hit as far as your modern cryptography is, look, can we do something with this? Can we do this, what do you call, a prime factorization given a very large number? Is it possible to do a prime factorization? Is this okay? So that's the question. So that's a problem which is very difficult to handle. The second thing is another one. What is that other one? Let's look at this. Suppose we say that let's look at this. Let's do this. Suppose we have, let's say 2 colors. Or let's say, why 2 colors? First, let's take 2 people. Let's take 2 people, A and B. Don't want to use this SMS jargon, otherwise it will become a problem. Tomorrow, my students will also write the same thing. Suppose we have A and B, 2 fellows. Trying to exchange some information with them. With each other. Now, what is that mathematics that they can do? So what they do is, we will look at this interesting combination. They basically, let's say they accept. They say that, look, we will choose, let us assume let them choose a modulus, common modulus. Say M. Now, after that, what we do? For this particular modulus, let them also agree upon the generator, the primitive root or the generator. There will be totient of n primitive roots for given n, but that n should also be of a specific type, otherwise it doesn't work. For the want of time, I will not look at it right now. Agree upon the primitive root modulo m. Now, what do they do is the question. Let's look at that. See, the thing is, when we try to, suppose you try to buy something over Amazon, you really don't know to whom you are going to talk to. You want to buy a product, and you're just going to order it at Amazon. The question is, do you really trust that fellow who's there at the other end? I don't really have to trust. Many of us don't even trust our friends or closer ones. Now, what we do? How can we trust somebody who is not even known to us? Can we give all our information to them? That's exactly where this idea of cryptography comes into picture. So now what we do? So they have, let's see what happens here. So they have agreed upon the modulus m and let us say a primitive root g. Okay. Now, what we do is, in most of the encryptions that people talk about, there is something called as a key exchange. Key exchange between 2 parties. For example, in olden days, I'm quite sure most of you would have at least heard this from their grandparents or probably even parents, where they used to send this postcard, an open postcard, which is a free for all to read. I mean, whatever comes in the letter, the postman will know first. So the moment the postman knows, if he's going to be your family friend, he will come to you and tell you directly. But if he's going to be someone who really wants to screw your sleep, you can always go around the entire village, tell about the letter contents, and then what he'll do? Later he'll come and give. By the time you actually know the letter content. So there is no secrecy in that at all. Whatever letter that you send by a postcard, there is absolutely no secrecy in it. Then came that inland letter where people used to, fold, close, and all those things. Then people cannot read. So we need to have some kind of privacy in the messages that we send. So now, how do we do that? A better way to do that is, say, so for example, I want to send some kind of a cash or some important document through somebody who I don't have to trust, to somebody who I trust. Suppose I have a very close friend of mine. I want to send a document to this guy. to my friend through an unreliable person, a highly unreliable person, what is it that I can do? I have to put this document, let us say, inside a suitcase. I will lock the suitcase with my key, and I can give the key to this person, the courier fellow, and say, you give it to my friend. But I don't trust him, so I cannot give him the key. So what should I do? The only way that I can send this, I have to go personally, give the message and come. Then there is no point in me looking at this encryption and stuff. So what do? I take a suitcase, I then put my lock, and then I send the suitcase along with this guy without giving him my key. Now it goes to my friend. Now what is my friend going to do? My friend is going to, he doesn't have the key, so he cannot take anything. So what he'll do, he will put his key, he will put his lock in that suitcase and then send it back to me through the same guy. Now what am I going to do? I will remove my lock because I have my own key. I'll remove a lock and then I'll send it back to this guy. So it will be a multiple pass message transmission system. And that's exactly what happens in what we call as key exchange techniques between two parties, which we call as Diffie-Hellman key exchange. Diffie-Hellman key exchange precisely works on this same philosophy that I just told you, which is also called as the briefcase protocol. It works on this. What is interesting is they choose this G and M. Now, what did we say? I want, say, A has to send a message to B through a courier boy, a courier guy, unreliable courier guy. So what does it do? Both of them, they have agreed that, okay, fine, I'm going to send the document, I'm going to put it in a box and then send it and all. Mathematically, what is equivalent to? It is equivalent to, say, looking at G and M. A and B, they send this information across the same channel. They send, and then they say G and M are the exponent and the modulus that you're going to work, the generator and the modulus that you're going to work with. Then what happens is very interesting. A does this. A chooses what we call as a private key. This is like taking his own lock and putting it in the suitcase. He chooses what's called as private key. Let's call that as let's call that as A itself. By X in front of us. Let's call that as A. A. Similarly, now what B does? B also has to put his lock, so B chooses his own private key and calls that as B. A does not know B and B does not know this A. Okay, capital A is the person, capital B is another person, small a and small b are basically the keys which only A and B, they know for themselves. A does not send this information to B and B does not send B this information to A. Now let us see what happens. Now what both they do, they basically do G power A mod M. This fellow does G power A mod M and sends it to this guy. And this fellow does G power B mod M and sends that number to this guy. Okay. Now, both of them have something totally different, which is not going to be of any help to them. But look at the very interesting trick that these guys do. As soon as this B fellow gets G power A mod M, he does this. He does whatever number he gets, he puts power B mod M. Now, what is that equivalent to? This is equivalent to G power AB mod M. Now, what is A going to do? As soon as A gets G power B, A does something interesting. He says G power B, the whole power A mod M. Now, what does that mean? I'm still going to get a G power AB mod M. You see, very interesting. G power A is some integer, which we call it, let's say, X. G power B is some integer, let's call that as Y. Y and X are basically transmitted over this insecure channel or whatever that we have. So, but then the courier boy will not be able to make it because of this. This is what we call as discrete log problem in your number theoretic and modern cryptographic sciences. What is that? Given X, given G, given M, it is impossible to find A. Similarly, given G, given M, given Y, it is impossible to find. That's the power of mathematics again. Is this clear? It is purely relying on the strength of mathematics. The modern cryptography actually lies entirely on the pillars of, the strength of modern security that's happening now is purely on mathematical properties. Of course, quantum is taking a major leap now, which means there are things which could go, weird. But then the moment Diffie and Hellman announced that, look, we have formulated, this is what we call as, this is going to be, say, some Z, and this is what is going to be used as a key for encryption. Okay, this is going to be used as a key for encryption. And they can do whatever they want. They can actually exchange the key. They can take a message and then multiply this with key and then send it to someone they trust, where the ciphertext is basically this. Then on getting, on the receiver getting the C, he can always do this. He can say M is equal to K inverse C mod M, where K inverse is typically the multiplicative inverse mod M. Multiplicative inverse mod M of what? Of K. That means we just saw K and M have to be necessarily relatively prime. So you have to choose your K and M in such a way that they are necessarily relatively prime. Okay. So this scheme is what we call as El-Gamal encryption scheme. The other one is even more interesting. What is the other one which is more interesting? That is what we call as our RSA encryption scheme, reverse Shamir and Adelman. The moment Diffie and Hellman came up with this, the moment Diffie and Hellman proposed to the entire world, saying that, look, we have identified a very interesting key exchange algorithm which cannot be broken. Reverse Shamir and Adelman, they were working, they were on their own individual result, but they came up and said, look, if this happens, then we can give an encryption scheme which can never be broken in polynomial time. And that's exactly where we land in what we call as reversed Shamir-Adelman encryption scheme, or the RSA encryption scheme. Now, this is deadly, in fact. It works on two interesting things. Let's see what they are. And let's see what RSA encryption scheme is all about. They do Diffie-Hellman key exchange, and then they do this encryption scheme in RSA. Let's see what that is. Just a minute. So what is this RSA scheme? So first step is of course, you will have Diffie-Hellman key exchange. And in RSA, what they do is they also do the same business. They take a modulus. This modulus is very interesting. What they do is you take two numbers, two very large prime numbers, P and Q, very, very large prime. Now what you do, take the product of this. Assume n is equal, fix n is equal to the product of this, P into Q. This is going to be the modulus that we're going to work with. Modulus, which is published. This n is publicly available. Modulus published. Okay. Now, what is interesting? P and Q are very large prime. Suppose you are given P, it will take you exponential time to find out what is Q. Suppose you are given, suppose you want to figure out which P and Q has given me this N, then you must have to check with each and every prime number till this large prime that you've taken, and you have to multiply with every other prime number, then check what is the modulus. Therefore, this N is equal to PQ. Choosing P and Q to be very, very, very large primes is very, very essential. Is this clear? It's quite essential. And this is basically chosen as the modulus. Then what to do? The one that is going to be, for example, if you're going to send me a message, what I'll do is I'll say this is the modulus and use this key. I will use a key E. This is the encryption key, which also I'll publish. Encryption key. This will be available in your browser. So what I'll do is, whenever you want to send me a message, you just do this. You just do M power E mod N. Mod N. You finish, you do this and then send me the ciphertext. Now, what is interesting? There are lots of things interesting here. What is that? N I know. Exponent I know. This also I know, because I'm going to transmit over an unreliable channel. What is it that I don't know? I don't know what to say. Now, how is the decryption done? The decryption is done in a very interesting manner. What does it do? It says M is equal to C power D mod N, where D is a decryption key, which is not known, not published. It's a private key. So RSA works with both private key and public key encryption. Okay. Now, what is interesting is, in case of Diffie-Hellman key exchange, we said that G power A mod M, G power B mod M. Let's call this as X. Let's call this as Y. Now, what did we say? In Diffie-Hellman key exchange, we claimed that knowing G, knowing X, knowing M, you cannot compute A in polynomial time. Knowing Y, knowing G, knowing M, you cannot compute B in polynomial time. Now, what we are claiming in RSA encryption is even more interesting. What is that? We say C is equal to M, I should not say E, C is congruent to M power E mod N. Now, what are we saying? We say that, look, that's an open challenge that math gives. N is known, exponent is known, C is known. You cannot find out M. So this is basically your RSA problem, because all these things, they work on what are known as one-way functions. So if you look at if I were to conclude this, since we just have another few minutes left, if I were to say that if there is something which is going to, which is still allowing us, to reliably, do money transfer from one account to another one, do online purchases and all those stuff, it is only math. It is math and math only, nothing else. So, it stands entirely on the strength of mathematics than anything else. See, it's an open challenge, right? I am giving you all these fellows. Try to find out this in polynomial time. No, it doesn't happen. Again, I'm giving you all these fellows. Now try to find out this M. Oh, it's just not going to happen in polynomial time, right? Therefore, if I want to capture the entire, secure system transfer, data transfer, money, whatever that you do now, if I were to capture, or if I have to have a tagline for, our secure system now, online or whatever modern secure system, it is just this. In math, we trust. Nothing else. I think this will capture the entire essence of our current communication, secure communication systems. It's been a challenge for even the what do you call the hackers to, because they have to really do a lot of the key space search itself is quite voluminous, that they'll probably it kind of becomes very difficult for them to break a system. Okay. I'm quite sure there are quite a few interesting videos and very nice intuitive materials which are available on the blog. I have on the web. I have just tried to cover as much as possible, probably throwing some interesting lights on prime numbers and stuff in the stipulated time that I had. But nonetheless, this could be a first step for you to explore math in more detail. Probably look at math as a more friendly subject rather than something that can be hated for. Okay, so I think with that I'll probably stop. I'll probably take some questions if people are up for it.
Yes, sir. Thank you, sir. We are just searching for questions in the chat box in the YouTube.
Okay.
Maybe they are finding it difficult to ask questions as well.
Asking questions is fine, but I just hope I don't get some royal bashing over there. That's more scary.
No. They are finding it difficult to crack down the questions.
They're probably, the reason is like, stuffing too much into this 1.5 hours, especially this. You remember we had done this like probably a one-day program or something where we started with basic number theory in the morning and afternoon we did this.
Yeah.
So it's probably an issue. Yeah.
Yeah, thank you very much, sir.
Okay.
In spite of your busy schedule,
I must say this time it is indeed, it is indeed a busy schedule this time.
You always accept our invitation. We are very much honored and privileged and happy that you are associated with us since a long time.
I hope the association continues. Exactly.
Yeah.
Thank you.
Thanks a lot for.
We'll always continue, sir.
Thanks a lot, sir. Thanks for the confidence and confirmation. Yes.
Sure. From my side.
Definitely.
Yeah. Thank you very much, sir. You started from starting basic numbers, prime, composite, and gave an application of all those to till RSA algorithm. It was a very beautiful and interesting talk.
Thank you.
On behalf of the department and myself, I thank you very much.
Thank you, sir.
Thank you. Thanks a lot, sir.
Yeah. So
with this, we'll end the session for today.
Okay.
All the participants, please give your feedback. The link is provided in the chat box.
And let me also apologize for the bad audio quality that you might have had in between, because I'm in some village where I have to really figure out the internet and then sit and do it. Okay. Thanks a lot. Yeah.
It was fine. No problem. I request all the participants to give the feedback. The link for the feedback is posted in the chat box in YouTube. Tomorrow, as usual, again, the second day, first session will begin in the morning, 11, and afternoon we will have. I request all of you to again join for the tomorrow session. With this, today, we end the session. Thank you, one and all.
Thank you. Bye, sir.
Yeah, thank you, sir. Thanks a lot, sir.
Thanks a lot. Bye, sir. Yeah.
Bye, sir. Bye.
Bye. Yeah.
The live event is over. Chat is no longer available.
Hey.